Hi, welcome again to our video series about statistics, and this is video 8. And in the last video we have learned linear regression, and today we are going to do the same thing, but this time we are going to use matrix algebra. And suppose that we have some kind of data points, and let me draw a scatter diagram. And this is x, this is y-axis, and suppose that we have some points for example we have 5 data points, and we want to find a line equation that fits these points. So we can have a line, I think like this one, and we have learned in the last lecture we have some errors and we call them residuals, right? So I'm gonna draw for each point. This point has this residual, and this point has this negative residual, and this point has this positive residual, and this one has this negative residual, and this one has this positive residual, right? And this line can be described by using a line equation which we called y hat, and this is the predicted values for y data points, and we can write this line equation by using b0 and b1 as constants and b1 times x, right? And this b0 is called intercept, which is the point that this line crossed the y-axis, and this b1 can be called slope or the regression coefficient, right? Regression coefficient. And when we find the values for b0 and b1, we can predict that all y values by using just a value for x. Okay, and to find the correct values for b0 and b1, we are going to use these data points, and we are going to minimize the error to find this line. So let me write this error function that we want to minimize. I'm going to write error equals the sum of the residuals, but be careful, before we take the sum, we are going to take the square of these residuals to get rid of their sign. Okay, so if we have negative residuals and if we have positive residuals, we don't want to take a direct sum of these residuals, and we can have some value near to close to 0, but still we can have some errors. So as a first step, we take square of these residuals and we get rid of their signs, and then we can take the sum of these residuals. So we are going to take the second power of these residuals to get rid of their sign. And let me write the residuals. This is the point y1, this is y2, y3, y4, and y5. So this sum is y1 minus y hat, my line equation for the point x1, and the second power square. This is the first error. Okay, this is x1, this is x2, this point is x3, this is x4, and this is x5. Okay, now continue with the second error. So y2 minus y hat, but this time for x2, and square of this error. And for the third point, we're going to do the same thing, y3 minus y hat x3 and square. And for the fourth point, y4 minus y hat x4 and square of this error. And for the last error, y5 y hat x5 square. Okay, now we have the total error and we want to minimize it. Okay, and I can write the error function by using di square sum of these error points, and I can use the line function now. So I'm going to take a sum starting from I equals 1 to lowercase n, and for this example we have n equals 5, and I have my line equation yi minus y hat xi square. Okay, and now I can use this equation for this part y hat xi, and I have my error now, I have my total error now equals the sum of the square of residuals, sum starting from I equals 1 to lowercase n, and yi minus b0 plus b1 xi square. Okay, now let me think about it. Now we have some total error and I want to minimize this error, and I have some data points. For this example I have 5 data points, so I have 5 sets of xi's and yi's. So I have x1, x2, x3, x4 and x5. So I have y1, y2, y3, y4 and y5, but as a variable I just have b0 and b1. So if we want to minimize this total error, we can change the value for b0 and b1. So I have a total error, for example, in the y-axis of this diagram, error, and let's suppose that we have b0 here. I have some error for some values for b0, and it changed when we change the value of b0, and I want to minimize it. Okay, so I have a function, I think like this, like this. Okay. For some values of b0 I have some error, and when I increase the value of b0 I have smaller and smaller total error, and at one point if I continue to increase the value of b0, and now total error starts to increase. So I want to find this value, okay, as my b0. I want to find the value which minimize the error. And also I have the same diagram for b1. So I have a similar trend for total error in the y-axis, and for this time b1 as a variable, so I have a similar behavior for total error as a function of b1. So still I want to find this point as an optimum value of b1. So in reality I have two axes. In reality I have two axes for my regression coefficients, and for this example intercept and slope b0 and b1, and these coefficients can be b0, b1, b2, b3. I have many of these, I can have many of these regression coefficients, and we will come to that, but for this example we just have b0 and b1. So I have an error function in, for example, z-axis, and I have two different regression coefficients. Okay, this time we have our total error here, total error, and we have our b0 here, and we have our b1 here. So we have a curve. Okay, we have an area, but a 2D curve. Like, I hope I can draw like we have some points for a set of b1, and also we have another set of another value for b1 as a function of b0. So we have a 2D curve. And I think we are gonna search a set of these regression coefficients. So we have to find the correct values for b0 and b1 to find the minimum error. Okay, for example, I can show you with a paper. So we have a 2D curve like this, and we are gonna search this point. Okay, so with this curve we can change the value of b0, and also we can change the value of b1, but we are gonna find the value, the set of values b0 and b1 to find the minimum error. Okay, so how can we find the values for b0 and b1 to find the minimum error, minimum total error? Okay, now we are gonna search this point, and we are gonna search this point, and from a geometrical point of view, at any point of b1, for example, we have a slope for this point. Okay, so we can find the tangent for this point, like this one. We can have a tangent like this for this point, and for example for this point we have a tangent like this, right? And for example for this point we have a tangent like this. But in this point, the point for minimum error, we will have a tangent, a slope like this. So in this point we will have the tangent equals to 0. So we are gonna search this point. we are going to search the value of b0, which we have the tangent of this point equals to 0. So from a mathematical view, we will find the first derivative of the total error regarding to b0. So we have b0, our variable, and we will take the first derivative of the error function according to b0, and we will have this first derivative equals to 0 to find this point. Okay, so we will have this equation. We will have our error here equals to 0. And for this equation, we are going to find this point, which we have our tangent is equals to 0 here. And also for b1, we will do the same thing. We are going to search for this point. So we are going to take the first derivative of our error function according to b1 now, and we are going to take an equation which this derivative equals to 0, and we will find the b1 which we have the minimum error. Okay, now I'm going to clear this area and I will write down the equations to find the correct values for b0 and b1. I hope you understand this concept. So now we are gonna take two derivatives of the error function for b0 and b1. So first derivative of error function according to b0, and for the second equation we are going to take a derivative of error function according to this time b1. Okay, now if we take a derivative of this function according to b0, and we will have this equation, right? Minus 2 and a sum starting from I equals 1 to lowercase n, and yi minus b1 xi minus b0 equals to 0, and also minus 2 starting from I equals 1 to lowercase n, and this time xi yi minus b1 xi minus b0, right? We have these two equations now, and if we have this left side of equation, we have this 2 minus here times this sum term equals to 0. So we can easily say this part equals to 0, right? Because if we multiply this term with 2 minus, so minus 2, so we still have this equation equals to 0. So this part has to be equal to 0, and also this part has to be equal to 0. So we have these two equations actually, and we can write these equations like this. You can write these equations like this. b1 sum of xi squares plus b0 and sum of xi's equals sum of xi times yi, and we have these sums starting from I equals 1 to lowercase n, and I'm not writing these details anymore. So sum of xi plus b0 n, and this n comes from I equals 1 to n xi power of 0. Okay, and we can write this term as n equals to sum of yi's. So we have these two equations. We have these two equations, and we have two different variables. So if we have two variables and if we have two equations, we can easily solve this equation system. If we have these points, if we have these 5 points, we can easily solve this equation system if we have two variables and if we have two equations. Okay, so all the things that we have to do is take a sum of x squares and take a sum of x points, take a sum of x times y's, and take a sum of x, and we already know the value of n, and take a sum of y points, and then we can easily find the value of b1 and b0. And also we can express this equation system by using matrices. How can we do this? We can write a matrix like this, and I'm going to use this color now. We can write this matrix by using the powers of x points and we will have a vector which includes b0 and b1 equals to this matrix. Okay, this is the same thing, right? This matrix equation is same thing with this equation system. It's the same thing. If we multiply this matrix with this vector, we will have this vector, and we can express these equation systems by using matrices like this one. And if we arrange the terms, and we can have a compact equation, and this time I'm going to use this color. We have lowercase n is coming from this term, and also we will have sum of yi's coming from this term. So we can use this matrix and sum of x points and sum of x points, sum of x squares. This is a matrix, and this is a vector which includes our regression coefficients, and this part equals to this vector. Okay, so we can find the values of B0 and B1 by just using the data points. Okay, we're going to take a sum of the data points and we find the values of B0 and B1. And now we can solve an example, and I'm gonna clear this page and I'm gonna use some data points. Suppose that we have suppose that we have 5 data points for X and 1, 2, 3, 4 and 5, and for Y points let's have 1, 4, 9, 16 and 25, and these points equals the squares of X points, but we are gonna find a line, so we will have some error like this. We will have an error for these data points if we use a line. So I'm gonna use the same matrix and then I'm gonna check my results by using Microsoft Excel. I'm gonna solve this matrix equation. So we have 5 data points, so we have our lowercase n equals 5. So we have 5 here, and we are going to find the sum of X points, and 1, 3, 6, 10 and 15, and also for this sum we have 15, and for the squares we're going to take a sum 5, 14, 30 and 55. Okay, we have our B0 and B1 here. We want to find these values, and for this part we're going to take a sum of Y points which equals to 55, and also for this term I'm going to calculate the sum of these values. Okay, so we have 9 and 36 and 100 and 225. Okay, we have this value. Okay, now I have my matrix equation, and I'm going to multiply this matrix with this vector, and I'm gonna create the equations. So we are gonna take a multiplication of this 5 and this B0, 5 B0 plus this 15 and this B1, 15 B1, which equals this 55. And then we are going to take a multiplication of this 15 with this B0 and this 55 with this B1, which equals 225. Okay, so we can divide these equations by 5 to find a simple equation set. I'm gonna use this color now. 1 over 5, and I think we have, when we divide this equation by 5, we have b0 plus 3b1 equals 11, and for this part we have 3b0 and 11b1, and what is it, 55? No, 45. Sorry, 45. We have these equations now, and then I can multiply this equation, this first equation, by minus 3, I think, and this time I have this set of equations, minus 3b0 minus 9b1 equals to minus 33, and we already have the second equation, and now I'm going to take a sum of these two equations to find the value of b1, and we don't have these parts now. We have 2b1 equals to 12, and we have our b1 equals to 6. Okay, now we can find, sorry, okay, sorry for the interruption. Now we have the correct value of b1 now, and we can use, for example, in this equation to find the value of b0. I'm gonna use this one, and b0 plus 3 times 6 equals 11. Okay, b0 plus 18 equals 11, and b0 equals to minus 8, minus 7, sorry, minus 7. And we have the equation now. We have y bar x equals minus 7 plus 6x. We have this equation. And let me create a scatter diagram. Okay, we have x, we have y, and we have this 5 points for x, 1, 2, 3, 4, and 5. And let's suppose that we have 5 here, 10, 15, 20, and 25. Okay, and we have our points. I'm gonna use this color. We have our points here, and I think something like this, and it doesn't have to be too precise, but I think it will work. And also this point. Okay, and we will have our regression line with an interception of minus 7 and with a slope positive 6 plus 6. So we have our interception point somewhere like this, minus 7, and we will have a line. I think we can check the value. For example, we can find y1 to just have 2 points to make it easier to draw our line. y1 equals minus 7 plus 6 times 1, so it equals to -1. Okay, so it's somewhere like this, right? Somewhere like this. So we have our somewhere like this. We have our these 2 points on our line, so we can use them to draw our regression line, and we will have something like this, I think. Okay, we have our regression line, and we just used our matrix equation to find the correct values of B0 and B1, and these are -7 and +6. And now I'm gonna check these values by using Microsoft Excel. And I'm gonna hide these handwritings, and I'm gonna close PowerPoint, and I will run Microsoft Excel, and I'm gonna use the same points to find the regression line to check my values of B0 and B1. Okay. I have my X points 1, 2, 3, 4, and 5. Sorry. And 1, 4, 9, 16, and 25. And I'm going to create a scatter diagram first. Like this. And then I'm going to select these points and right click to these points, and I'm going to add a trend line. And yes, I want to see the equation, and I want to see also R square value. Okay. It seems we have the correct values, right? And this gives us the equation, and I think you cannot see. Okay. We have this equation, y equals 6x minus 7, which equals to our points b0 equals -7 and b1 equals to 6. And also it's a very accurate line which has r square value 0.9626. But obviously these points fits to a second order polynomial. So we have to have an equation like y hat equals b0 plus b1x plus b2x square. So it will be a second order polynomial, and this is the subject of the next video. It's a very good point to stop here, and I will see you in the next lecture. Take care of yourselves and stay at your home. See you later.